The title of his talk is Mean Curvature Flow in Surgeries.
Thank you very much for the kind introduction, and thank you very much for the great honor to give this lecture. I still remember with great joy my previous visits to this institute and also to the university, in particular this long stay in 1999 and 2000. It's wonderful to be back. Thank you. So I would like to talk about joint work with Carlo Sinestrari from Rome on mean curvature flow, where you deform a surface in Euclidean space or in an Riemannian ambient space according to its mean curvature. And the underlying idea behind it is the heat equation. So let me just show on two transparencies the basic properties of the heat equation that we should keep in mind. You have a heat equation with some initial data, and then the heat equation will smooth out these initial data. And if, for example, you prescribe boundary conditions, it will go to an equilibrium, to a stationary point of the flow. Important is it is the gradient flow with respect to the L2 norm of some energy, in that case, of course, the Dirichlet energy. The other thing you should remember about the heat equation is that it's absolutely crucial to understand the self-similar solutions of the flow that relates the properties of the heat equation to the geometry of the space, say in Euclidean space. You have rescaling property in the solution present, and with this rescaling imminent in the solutions of the equation, you also get optimal estimates on the regularity of solutions. So the key thing to remember about the heat equation is that it has a smoothing property. Even if you just know that the sup of the function is bounded for some reason, then the derivatives of any order are bounded with precise powers in time, even though they might not be bounded at initial time, and you have nice scaling invariant estimates which are known to be optimal. Also, you have certain positivity properties of the heat equation. There's a Harnack inequality. If you have positive solutions, then there's a Harnack inequality that tells you that the solution cannot fall off from its maximum too quickly. We have a lower bound on ddt of log of u, and this simply says that things cannot cool off too quickly, and this has again to do with the property of the ambient space, of course. Now, when geometers saw this picture, I don't know who saw it first and applied it to geometry, they said, oh, this is a nice way of deforming a curve into a nicer curve. But of course, in geometry, you don't just want to deal with functions, you want to really deal with curves, and curves that are not easily written as graphs over a line. So you would like to deform more complicated curves. And then when you apply the idea of heat equation to the curve, then you end up with a different energy. You just take the length of the curve to be the energy and try to decrease that as quickly as possible with respect to the L2 norm. And then you again get a second order parabolic equation, and instead of the Laplacian on the right hand side, you now take the curvature of the curve times the normal direction to the curve, such that the vector k times nu is the Laplacian of the position vector of the curve, second derivative with respect to arc length. But it's not a linear equation because the arc length, of course, depends on the evolving curve. So it's a quasi-linear system for the position of the curve in Euclidean space, which is the best analog of the heat equation I had on the previous transparency. But it's now nice geometrically invariant equation which should have nice properties. And indeed, there's a famous theorem by Matthew Grayson, building on previous work of Michael Gage and Richard Hamilton, and they show that if you take an arbitrary closed embedded curve in R2 and you let that evolution equation curve shortening flow deform the curve, then it will completely unwind, no matter how complicated it was at the beginning of the deformation. So it will eventually, after some finite time, turn this complicated embedded curve into a convex curve, and the embeddedness is never violated. In view of the maximum principle, you can easily show that. And in fact, at the end, it contracts nicely to a round point, becoming more and more round in the limit. Well, I think I have an easy proof. Grayson's original proof was sort of counting the inflection points and showing it was decreasing and sort of really following the curves point by point. What I want to stress is that there's a better idea of proof, and that's at the bottom of this transparency, and it's sort of a recipe how you should use heat equations in general, Ricci flow, mean curvature flow, to understand the shape. Namely, you don't look at the curve at each time and try to control carefully the shape of the curve at each time. You only look at the singularities, because as long as the thing is smooth, the curve provides a nice diffeomorphism, the flow provides a nice diffeomorphism of one curve to the other, and you only have to check what happens if something goes wrong. So you just analyze the singularities. So what one does is one shows there has to be a singularity in finite time. That's true because you could put a circle around it that has to collapse in finite time and is a barrier. And then you show that a singularity can only happen if the curvature goes to infinity. It cannot happen that the curvature is bounded and some higher derivative blows up. That is the regularity property that I pointed out for the heat equation in general. It transfers to this nonlinear equation. So you just analyze those points where the curvature blows up at some finite time, and then you prove something about these singularities. You rescale and you analyze the limiting shapes, and you analyze all these shapes, and it's not too hard in this one-dimensional case to see that the only embedded limiting shape is a round circle. There's one global estimate going in there that I don't have time to discuss, but the idea is analyze the final moment and analyze what you get there. If you see the circle, then you've already proved the theorem. So that's how you can use analysis, blow-up techniques to analyze the behavior of this one-dimensional flow. Now,
did you say there's monotonicity? This is encircled by another curve. The encircling one would.
If you have two solutions of curve shortening flow which are disjoint at time zero, they will remain disjoint. So if you put a circle around it, you have an exact ODE telling you how the circle shrinks in finite time to a point, and that's then the time where at the latest the other curve has to have a singularity. It's just like for the heat equation. If you have two different initial temperatures in this room and you have no heating, it's just the ordinary heat equation, then if one temperature is bigger than the other, it will remain bigger as time goes on. So this principle transfers to these curves. Now, the mean curvature flow is just the curve shortening flow in higher dimensions. Instead of the one principal curvature, you now have many principal curvatures at each point of the surface. You sum them up. That's the mean curvature of the surface at each point. And you move again in normal direction, with the mean curvature being the speed. And this is on the right-hand side. If you differential geometry, you see that this mean curvature vector is the Laplace-Beltrami operator of the position vector at that point of the surface, but the Laplace-Beltrami operator taken with respect to the induced metric, making this again a quasi-linear system for the position of the hypersurface in space. The flow is again a gradient flow of area. In this case, it's the fastest way with respect to L2 norm to decrease the area of the surface.
When you speak of gradient flow, what is the metric?
I'm not really saying gradient flow in the space of all objects. I'm just saying that if you look at all normal velocities with the same L2 norm, then this is the one that this flow is the one that decreases the area the most. That's just Hölder's inequality. Now, when you look at this quasi-linear system, of course the position determines all the other geometric quantities. So by differentiating, you can find out what is the time derivative of the unit normal, what is the time derivative of the measure, time derivative of the second fundamental form. When you do that, you get a system of equations for the components of the second fundamental form, or in this case I've written it for the Weingarten map, the components of the Weingarten map. And what you end up with after some computation is a reaction diffusion system for the components of this second fundamental form. A squared is the total norm of the second fundamental form. At each point it's the sum of the squares of the eigenvalues. The Laplacian is again the Laplace-Beltrami operator on the surface, means the trace of the second covariant derivatives with respect to the induced metric at time t. So what is important in this equation is that you have the Laplacian for each component of the second fundamental form. So it's a diagonal system where you have the same rate of diffusion in all directions, making the maximum principle applicable to this kind of system. The other thing that is important is that you have this nonlinearity cubic terms on the right hand side that mix the principal curvatures, and these cubic terms of course determine what happens to the geometry of the surface as the evolution goes on. And another way to look at it is also that the diffusion term is the nice term. That's the one that helps you and smooths out and is sort of responsible for this nice parabolic properties of the flow, whereas the reaction terms can kill you because they can cause singularities. They are the terms that make the circle shrink to a point in finite time, and you often find that there is a competition between these two terms which you have to carefully analyze. Often you find that in a singularity the diffusion term is too weak to prevent the singularity, but on the other hand the diffusion term is still good enough to make the singularity in some sense uniform and nice and self-similar. So that's important to keep in mind. It's a reaction diffusion system for the curvature, and it should be compared with what you get for the Ricci flow that was used by Hamilton and Perelman for the proof of the Poincaré conjecture. In the Ricci flow, the picture looks like this. You have an abstract Riemannian metric, Gij, on some three manifolds, say, and you evolve the metric in direction of the Ricci curvature, starting from some initial Riemannian metric. Now in harmonic coordinates, the Ricci curvature is something like the Laplacian, so again you have a quasi-linear parabolic system. And when you do the calculation there, you also get a reaction diffusion system for the intrinsic curvature components. And it's again, the leading term is diagonal, and it's again the Laplacian on all the components, and it's a reaction diffusion system, but now the terms in the Riemann tensor are quadratic. If you think about it, that Gauss curvature scales like mean curvature squared, it's exactly the same scaling actually as this reaction diffusion system. But the algebra is different. These quadratic terms have a very different structure than these cubic terms in mean curvature flow. For example, I've written down for you in 3 dimensions if the M1, M2, M3 are the sectional curvatures of the 3 manifold, how this reaction diffusion system looks. And it turns out that many of the properties, while different, are analogous for Ricci flow and for mean curvature flow. Let me illustrate this by showing you some old theorems on these two flows, namely the case where you have positive curvature. And the famous paper by Richard Hamilton in 1982 states that if you take a 3 manifold closed with positive Ricci curvature, then the flow will contract nicely until the volume reaches 0, and if you rescale, you find a constant curvature metric on the 3 manifold. So it's a length space, or if it's simply connected, it has to be S3. Now, the first result for mean curvature flow is completely analogous to that. It works in any dimension. It says that if you start with convex surfaces, then this is what happens. The surfaces shrink to a point. The area and the volume tend to zero. In the process, the surfaces become round. And you get a result which is analogous to Hamilton's Ricci flow result. Now, as soon as you go away from the positively curved situation, both in Ricci flow and in mean curvature flow, the deformation of the geometric objects will form singularities. And I think it's really useful to consider both flows at the same time, because one is sort of the intrinsic version, intrinsic geometry version, that's the Ricci flow, and the other one is the extrinsic.
What was different from 1 in 2 dimensions and 2 and 3? What's sort of, you're saying now singularities form while Grayson said they didn't form.
In 1 dimension, it is easier to get the singularities. You prove, for example, the singularities, they have to be self-similar. That's just an ODE for the curve in the plane. You analyze that ODE and you see the only solution that closes up and is embedded is a circle. Now, in higher dimensions, it's much harder. So you will have many more singularities. I show you some more. And that's why in higher dimensions, I need a curvature condition to get such a result similar to Grayson's. Sorry? Right, Navier-Stokes in 2D. It's a big step. Peter, it's a big step from 1 dimension to
I'm asking just something much more basic. What is it about what you're saying? I think that singularities form in 3 in higher dimensions, and they don't. Grayson's theorem, they didn't form.
No, they do.
They do. It still goes to a point. But they're simple. That's the only one.
That happens. You say, okay, maybe you're going to say the same is true in higher dimensions.
I'm saying for convex, if it's convex, the same. If it's not convex, much more complicated things happen. For example, all right. So the spherical. Oh, there's an H missing. The spherical case is the singularity that happens for convex surfaces. But in higher dimensions, you have the possibility, for example, to put an initial surface which has a neck, and then around the neck, if the neck is long and thin, the curvature around the neck is huge compared to the curvature along the neck. Therefore, the mean curvature is strictly positive and pushing the neck inwards. Whereas in 1 dimension, this can't happen. The curvature is pushing out. Yeah? So you get singularities where thin necks shrink off, and under the microscope, it turns out you can prove in these cases that if you rescale, you get a self-similar shrinking cylinder solving mean curvature flow, which has a circle as its cross-section or a higher dimensional sphere as its cross-section. Now, there is one other singularity that I have to tell you about, which will occur, and that is if you try to interpolate between the 2 first possibilities. So if you take a surface which has a neck, but the 2 sides are unbalanced, one big sphere attached to a small sphere, if you do it just right, then you get a surface which doesn't know whether it wants to become convex or whether it wants to have a neck pinch. If the small bubble is very small, then it will just zip through and you get a convex surface and you're back in the old picture. If the second bubble is of equal size as the first bubble, you get a decent neck pinch which looks like a cylinder. But if you sort of are very unlucky and you've picked an initial surface which is just in between, then you can have a neck pinch which just doesn't quite make it. The little bubble gets stuck and you form a horn. And if you rescale this horn at the tip, what you see is not a self-similar shrinking solution as in the first 2 examples, but you see a self-similar translating solution. You get a non-compact translating solution of mean curvature flow. And the amazing thing is that exactly these three pictures also happen if you take Ricci flow for three manifolds, or if you take Ricci flow for four manifolds with positive isotropic curvature. So these pictures, I can use the slide for a lecture on mean curvature flow and for a lecture on Ricci flow. The picture is the same. The quantitative details are different, of course, but the pictures are the same. These canonical singularities occur both for Ricci flow and for mean curvature flow. Now, the hard part is to show that in a given situation, these are the only ones. Right? You would like to identify situations where these are the only possibilities. And it turns out now, for example, for mean curvature flow, also for Ricci flow, if you go in higher dimensions, many more, even worse possibilities can happen. Much more complicated singularities can occur where we have nowhere near the technology of analyzing them or even proving that we can extend beyond these. But these singularities are sufficiently simple that we have a chance to possibly extend the flow beyond these singularities by cutting through the neck or by cutting off the horn and then extending the flow. Now, the
Question. So in the second theorem here, when you say convex hypersurface, is really all eigenvalues of second fundamental form are non-negative?
this is a compact. This is for a compact surface, a closed surface. And if all the principal curvatures are non-negative, then you can see from this reaction diffusion system here by the maximum principle that they remain non-negative. And there's even a strong maximum principle, so they turn strictly positive. So if for each positive time, the surface will be strictly convex. And then you can prove that, in fact, it remains uniformly convex. Each eigenvalue remains a fixed multiple of the mean curvature, and then you sort of work on that.
But then the two theorems are not really parallel in a way, right? Because in the first one, this is Ricci. Okay, so it's possible compensation between sectional curvatures. In the second one, all curvatures have the right sign.
Well, in the first one, all the eigenvalues of the Ricci tensor have.
Okay.
Yeah. Right? In fact, that was a sensation at the time because people couldn't even classify all three manifolds of positive sectional curvature, so that this method worked just assuming positive Ricci was sensation. Yeah. Okay. Now, so based on this knowledge that these singularities occur, and hopefully they are the only ones, Hamilton in the 90s, the early 90s, put this idea how to exploit this behavior possibly. Namely, he said, suppose we have only these canonical singularities in a flow, be it Ricci flow or be it mean curvature flow. Let's flow until we find these pictures, and then whenever we find a neck, just cut it out, replace the two ends of the neck by spherical caps in a nice way, or replace the horn by a spherical cap. Do this in such a way that the surface really gets better, and I mean better from an analytic point of view, that the surface gets better in the sense that the curvature, say, drops by a factor of 1,000, and then restart the flow from there, and hopefully you can prove this happens only finitely often, and after you've done it finitely often, you have a final singularity where you actually recognize the pieces to be spheres or possibly products of Sn-1 cross S1. So that, or in the Ricci flow, of course, flow may go on and produce all the shapes that are in Thurston's geometrization theorem. Now, Hamilton pursued this concept very far, and the big problem in the Ricci flow was the possible deterioration of the cross-section of one of these necks. Right? So if you have a three-manifold and you form a neck, you would like to have a nice neck with a round S2 in the cross-section of this neck. The problem was that this S2 might have deteriorated and produced sort of a cylinder with two caps at the end. He called one end of this cylinder a cigar solution. So you would have a three-manifold which doesn't have a nice neck to cut, but which looks like a two-dimensional, like a cross product of a one-dimensional line and a two-dimensional, very thin and long cigar. Now, what goes wrong with this picture is that there is volume collapse and that the injectivity radius deteriorates, and we know that Perelman found a method to avoid this collapsing property. Now, in the mean curvature flow, it turns out you can put a condition which prevents this kind of collapsing. And you can do it with a curvature condition. So, and it turns out the right curvature condition that you have to put is you put not convexity, you weaken convexity essentially by one step. Instead of asking that each eigenvalue of the second fundamental form is positive, you ask that any sum of any two eigenvalues is positive. Now, this condition is just strong enough to rule out that you have a piece of the surface which looks like R2 cross Sn minus 2, because then you would have two flat directions and sort of a sheet of bubbles. Now, and you definitely have to rule that out because that singularity can occur, right? A sheet R2 cross Sn minus 2 and the Sn minus 2 shrinking under mean curvature flow, self-similar. That's a well-known, nice, self-similar shrinking solution of mean curvature flow. So you're certain that such singularities will occur if you don't rule it out. So this condition, lambda 1 plus lambda 2 positive, is made to rule out these sheets of collapsing bubbles. It makes sure that you can have only one straight direction, and one straight direction corresponds to next. So the hope is that if you impose this initial condition, that you get only those canonical singularities that I showed you in this one transparency. And indeed, that's exactly the theorem I was able to prove with Carlo. If you have an initial surface which is too convex in this sense, then the only singularities are canonical. That is, you can have shrinking spheres, or you can have a neck, or you can have a horn. And now this is completely analogous to Perelman's result, where he ruled out this collapsing here, and this was the only remaining case. So after Perelman had ruled that out, only the canonical singularities are there. So in some sense, you can see Perelman's result on ruling out the sheets by looking at the injectivity radius as analogous to this one. Of course, the nice thing is that in Ricci flow, in three manifolds, you don't need any curvature condition to prove that. There's no curvature condition. It always works that you have only these canonical singularities. But for mean curvature flow, you do need it. And the reason is, of course, that if you have a three manifold sitting in R4 as a hypersurface, any S1 that's in there has curvature. But an abstract three manifold has no intrinsic curvature along an S1. So that's why the Ricci flow is nicer. It's nicer behaved on three manifolds than mean curvature flow. Now, the step of analyzing the singularities and classifying them, once you have reached this level, that you've only these three canonical singularities, you would like to extend the solutions by surgery beyond these singularities. And in the Ricci flow, this was achieved first for four manifolds of positive isotropic curvature, and then, of course, by Perelman for three manifolds. Hamilton's result of 96 is one dimension higher. So he's in the situation where the cross-section is an S3. That gives it some more rigidity than in 3 dimensions, where the cross-section is just an S2. What do I mean by rigidity? When you are in 2 dimensions, you can have a surface of positive Gauss curvature, a 2-sphere, where the Gauss curvature is different everywhere. If you're 1 dimension higher and you have a surface where all the Ricci curvatures are the same positive number at each point, then they have to be constant across the surface. So then you have a round sphere. So this makes the analysis of necks of 4 manifolds, where you have these 3-dimensional cross-sections, easier than 1 dimension lower, because you can play off the 3 eigenvalues of the Ricci tensor against each other and exploit this extra rigidity coming from the Bianchi identities inside that 3-manifold. Now, Perelman was able to do that analysis even in 3 dimensions using his entropy. I don't have time to go into those ideas. But the point is that in both cases it was possible to analyze the asymptotic behavior of these necks, both in the neck and in the horn case, to such precision that you could do this gluing of this cutting and gluing of a spherical cap in such a way that you can extend it beyond the singularity. And it's important to note that these surgery constructions were done in a precise quantitative way. I mean, I've only drawn picture, but you really have to say in which C, K, alpha norm are you close to the cylinder, and what exactly is the gluing formula for your spherical cap that you attach to the cylinder, because you have to make sure that all your a priori estimates that allowed you in the first place to characterize these singularities, that they survive the surgery. If they don't survive, you might have to do the surgery infinitely often. So you have to make sure that all the a priori estimates survive the surgery, so that the surface really improves and that you can then show there are only finitely many surgeries necessary, for example, by arguing that each surgery eats up a certain amount of volume. There's only a finite amount of volume available. Yeah? So there's a quantitative, precise procedure for Ricci flow in these 2 cases. And the main result I would like to tell you.
So Perelman's work also works for 4-dimensional Ricci flow? In this work
I meant this for 3 dimensions. Yeah. Now you can, of course, use Perelman's construction, which is slightly different from Hamilton's, also in the positive isotropic curvature case in 4 dimensions. Now the main theorem I want to state is that this works in any dimension for 2 convex surfaces if the dimension is at least 3. Right? So you start with any 2 convex surface in Rn plus 1, n is at least 3, and then there is an algorithm where you run mean curvature flow, you stop it just before the singularity, you do surgery, you run it again, do surgery when it's necessary. I explain it in more detail in a minute. And you only have to do this finitely many times, and then all the area of the surface is used up. Now, as a corollary, because we only get pieces that we recognize, namely in the end, in the singularities, we find only finitely many spheres or copies of Sn-1 cross S1, we can conclude backwards what the original surface had been. And one corollary, for example, is that if you have any surface in Rn plus 1, which is 2 convex and closed, then it has to be a finite connected sum of copies of Sn-1 cross S1, or a sphere, if it's trivial. Well, in particular, this implies if it is simply connected, it has to be the sphere. So that proves, for example, for n equals 3, for n equals 3, it proves the a special version of the Schoenflies conjecture, if you like. Any two convex surface, three-dimensional surface in R4, which is embedded and simply connected, then it bounds a smooth ball. It's still open if you can drop the curvature condition. But at least under this condition, you will get this. In fact, this means you not only control the diffeomorphism type of the surface, you also control the diffeomorphism type of the enclosed region. So the region is a handle body because you can really keep control of the topology, also of the region inside, because, and this is wonderful that I can say this in this lecture, because the time, of course, is a Morse function, giving you complete control of the interior region as the surface contracts to zero area, zero volume. Now, what is the strategy of the proof of these results in the case of mean curvature flow? So here comes the analysis core of the matter. So you have to establish a sequence of a priori estimates, and you do it at the curvature level. So the first few estimates just tell you that things don't get worse. So you show that positive mean curvature is preserved, you show that two convexity is preserved. That just works by using a maximum principle on this reaction diffusion system I showed you at the beginning. More importantly, in the second step, you show that they stay nice, things stay nice in a uniform way. So if you have positive 2 convexity, so lambda 1 plus lambda 2 is positive and the surface is compact, there must be some epsilon that lambda 1 plus lambda 2 is bigger than epsilon times h. This remains true with the same epsilon. So you have sort of uniform 2 convexity across your whole flow. And you can actually show that in the surgery construction that you have to do, this estimate is easily preserved also, because you replace a cylinder, after all, by a spherical cap. So this estimate will not be violated by any kind of surgery. H is the sum of all of them. Since we are in the setting of 2 convex surfaces, the sum controls everything. So there is a constant such that the a squared, the full norm squared, is bounded by a constant times h squared. Yeah, so we can really use h as a detector how singular is the surface at a given point. Now the estimates C and D are really the heart at the curvature level. They tell you things get better. So the first one, the C, tells you that the surface becomes convex near a singularity. Namely, the negative part of the second fundamental form, the negative part of the lowest eigenvalue, lambda 1, is tiny. So lambda 1 is larger than an arbitrarily small negative fraction of the mean curvature minus some constant, just depending on this eta and the initial data. So this eta, that I can choose the eta arbitrarily small, that breaks the scaling invariance of that inequality. So that tells me that if I rescale the singularity, if I blow up, that the eta term, since I can choose the eta freely, I can make it go away. That means after rescaling, lambda 1 is greater or equal to 0. This is exactly what happens in the neck pinch. If you rescale in the neck pinch, you find a shrinking cylinder. The cylinder is not strictly convex, but it's weakly convex. And lambda 1 is the 0 eigenvalue going along the cylinder. So this estimate is the first one that says things are really improving. Actually, Carlo and I can prove this estimate without assuming the 2 convexity. So just positive mean curvature, just starting with that very weak positivity condition, positive mean curvature makes sure that in a singularity all the eigenvalues are non-negative. Now, D uses two convexity. D is an estimate that tells you that, now suppose we run into a singularity, and suppose we are not in the situation where we have something uniformly convex, something which converges to a sphere. Suppose we are in the unlucky situation that indeed one eigenvalue is very small. Suppose lambda 1 is small compared to the rest of them, to the mean curvature. Then the others have to be close together. Right? So if one eigenvalue is very small, then we would like to show we have a round cross-section. So the thing to prove that at the curvature level is to show that if one eigenvalue is small, then the n-1 other eigenvalues have to be close together, and I've expressed this by saying the difference of the largest and the second smallest is less than eta times h, and eta is a number arbitrarily small. So again, I break the scaling invariance in this estimate. So if I were to rescale such a singularity where lambda 1 gets smaller and smaller compared to the mean curvature, then I can find at the same time that after rescaling it must be a cylinder, because there's a cross-section where all the eigenvalues are the same. And now you see why I need n greater or equal than 3, because I need at least two directions in my cross-section. The Quadratic equations otherwise don't tell me anything, and I might end up with a one-dimensional complicated curve cross a cylinder, so for a two-dimensional surface in R3, and the proof wouldn't work. So this last step, giving me the round cross-section, that's where I need n is greater or equal than 3.
But you also have C eta. C eta here.
Right, but C eta is scaling. It only depends on the initial data, and the initial data, it depends on the curvature of the initial data, which is bounded. So when you rescale near the singularity, the C eta goes away. Now, after you've done that, you now know that at each point where the curvature blows up, things look like you want them to look at the curvature level, namely either strictly convex, or you find this point which looks at the curvature level like a cylinder. Now that doesn't help you at all if near such a point there's another point where the mean curvature is very small and you don't get the same picture. Because it doesn't help you if at one point the curvature looks like the curvature of a cylinder. That doesn't help you to find the cylinder. You have to find this neck. So to find this neck, to have neck detection, you need to know that this curvature picture is true in a sufficiently large neighborhood that it covers at least one round, one tour around the cylinder, so you can detect this neck. Therefore, we need a gradient estimate. We need to know that this picture, which we detect at some point where the mean curvature is huge, remains true in a sufficiently large neighborhood around that point. In the Ricci flow, that is achieved with a Harnack inequality. For the curvature, you show the curvature cannot drop off quickly enough, too quickly from a maximum point or from a point which is very large, and that led to all the complications finally needing the entropy estimates. It turns out that in the case of two convex surfaces, we can do better. It turns out there is an explicit a priori estimate for the gradient of the second fundamental form, which scales right. So we don't have to do these arguments for which such an estimate, such a direct a priori estimate for the gradient of the curvature is missing in Ricci flow. And when you look at the work of Perelman, a huge part of the work is devoted to arrive at such an estimate eventually with the help of contradiction arguments, approximation levels, 12.4 or something like that, right? So the key here is that we have a direct a priori estimate that takes us from these four estimates at the curvature level to an estimate at the gradient level. And it's scaling invariant, scaling with the correct way. So it tells us that if this picture happens, it will happen in some neighborhood. And this allows us to establish then that if the mean curvature goes to infinity somewhere, that either the surface is strictly convex there, or that there is a neck. Now, the trick there is, however, that there's one more difficult. Remember that I showed you three singularities. I showed you the shrinking sphere, I showed you the neck, and I showed you the degenerate neck extending into a horn. Now, if you're so unlucky to see the maximum of your mean curvature at the tip of the horn, of course you don't see the neck. So the neck may not be right at the point where the mean curvature tends to infinity. You may have chosen the wrong point. So there's an extra step in there where you have to prove that, well, either you are in a situation where it's uniformly convex for quite a distance, and then it has to close off by an argument like Meyer's theorem, and then we are in the sphere case, or you can find nearby, not too far away, points where the curvature is small, so that you can't apply Meyer's theorem. And if you find such a point where the curvature is small, then you are in the situation of estimate D. One curvature is small, then the others are equal to each other, and that persists in the whole neighborhood, and then you find the neck. That's sort of roughly what happens. But you really have to do these estimates in such a way to exploit or allow for all three possibilities. You may sit on a point which goes to a sphere, you may sit on a neck already, or you may sit on the horn and first move over before you find the neck. Once you found the neck, in the last step, you then have to control the neck really in C2 alpha norms in great precision and actually do the surgery. Do it by hand, bend the cylinder inwards and attach a spherical cap. And the theorem says, yes, you can do that. So if the dimension is at least 3 and the surface is too convex, then you can find finitely many times, depending just on the initial data, and you can find manifolds modeling the flow between these surgery times. And in between the surgery times, you have smooth immersions solving mean curvature flow, completely smooth solutions of mean curvature flow. And these different smooth solutions of mean curvature flow are attached to each other exactly in the way I've described. If you come to the end of one time interval, if you approach a surgery time, T alpha plus 1, then you get the new surface schematically by either replacing a neck by 2 spherical caps, or by replacing a horn with 1 spherical cap, or if you found a sphere, you just throw it away because that's a piece you allow, or if you find an Sn minus 1 cross S1, you also throw it away because it's one of the building blocks we expect. Actually, it can happen that you end up at a singularity and you find this neck and you begin following the neck, and the neck will go on and go on and go on. That's how you actually do it technically. You find this neck at the first time and then you follow the neck. And as the neck goes on, it cannot go on forever because there's only a finite amount of area. So if it closes in itself, that's one possibility, then you found an Sn minus 1 cross S1. Right? If it doesn't close in itself, you have to prove that it closes off in a convex cap, that would be possibility B, or that it opens up, that would be possibility A, or the left-hand side of possibility B. So the point is that you can analytically really do this. The a priori estimates are sufficiently strong to give you enough control to really follow the neck and establish that only these possibilities occur, and that as you approach the final time, you only see pieces which we know, Sn or Sn minus 1 cross S1. In other words, you prove that there is simply not enough area left to form any one of the other singularities. So in the end, you prove that you use up all the area. Now,
Is there a part here that says you need to add a certain amount in each step?
right now that comes. That step is the crucial thing here, and this is actually somewhat different from what Perelman does. The crucial thing here is that the surgery can be done at a uniform radius, which is only determined by the initial data and just doesn't change across from one surgery to the other. In other words, you would be lost if after the first surgery you have to do it in a neck of size 10 to the minus 3, and the next one 10 to the minus 9, and so on. So you have to show you can do it at a fixed rate. But the hard part is then to show that when you do the surgery, you really drop the curvature by a fixed factor. Because that then tells you that until the next surgery, a certain time must have elapsed because of the general smoothness properties of parabolic equation. In other words, you have to, in the surgery, you have to do it so well that the patient has healed until the next surgery is due, right? Okay. Right, at the technical level, here I showed you the estimates, but how do you do it technically? Technically, to get the convexity estimate, you have to look at the elementary symmetric functions of the principal curvatures, and you actually prove lower bounds on all these elementary symmetric functions iteratively. That's how it works. And when you get a lower bound on the last one, it implies a lower bound on lambda 1. The roundness estimate then is also dealing with PDE techniques. The roundness estimates you do by looking at this quantity. You take the full norm of the second fundamental form, you subtract 1 over n minus 1 times the trace squared. This is a quantity that would be 0 on an n minus 1 dimensional sphere. So this quantity is going to measure the roundness of the cross section if lambda 1 is equal to 0. That's the idea. And you prove that this quantity satisfies such an estimate by looking at the quotient of this quantity divided by h to the 2 minus sigma, and then you really use PDE techniques, Morse iteration or lemma of Stampacchia. You use Poincaré inequalities. You use in particular the uniform Sobolev estimate by Michael and Simon, which, by the way, is not available in Ricci flow. You have to use the diffusion terms in a substantial way to get this estimate. I should point out that a lot of estimates in Ricci flow come just from the reaction terms. The reaction terms help you. In the mean curvature flow, that's not the case. The reaction terms don't hurt you, but they don't help you. You have to get all improvements out of the diffusion terms. That's why you need integral estimates to get this. You have to use the Sobolev inequality, otherwise you have no chance of establishing these estimates. But there's a major difference to Ricci flow. Now, I want to say something about the gradient estimate, because I think that's a particularly nice thing. Once you have the convexity estimates and the roundness estimate, you go for the gradient estimate, you establish a parabolic equation for the gradient of the second fundamental form, and you have on the right-hand side a terrible term that blows up in a singularity, curvature squared times the gradient squared. So you have to absorb somehow this terrible term on the right-hand side. And the way to do it is to exploit the roundness estimate. And I think this is interesting how that works. So you take this quantity that by the roundness estimate is positive. Right? Here's the roundness estimate. The roundness estimate tells me that this quantity g is positive. G has a nice evolution equation where I have a good gradient term, and I can divide by G. So I use the fact from the roundness estimate that I get a nice quantity that I can divide by. When you work it out, this gradient term here will help you if it's positive. and it can be used to kill off the bad gradient term in the evolution equation of gradient A squared. Why can you use this term here? Why is that a good term? You will say, well, in the general Schwarz inequality, the gradient of a tensor squared is bigger than 1 over n times the gradient of the trace squared, but not bigger than 1 over n minus 1. All right? 1 over n minus 1 seems to be too big. Now the point is that gradient A, because of the Codazzi identities, has not just interesting traces over the last two indices, which is A, but also interesting traces over the first and the second and the first and the third index. So if you decompose gradient A into its irreducible components, you get a better inequality than Schwarz inequality. You get a bigger constant in front of gradient h squared than 1 over n. And the miracle is that if n is greater or equal than 3, this constant is bigger than 1 over n minus 1. That's why this is a good term which you can combine with gradient A squared in order to get a gradient estimate. So that's the way where you get a direct link from the curvature estimate to the gradient estimate. Such a link is so far not known for Ricci flow. Now, once you have all the a priori estimates, the final work is in really determining the scale where you do what. So the a priori estimates help you first to determine the curvature scale where you have complete control. Let's call it the control scale. If the curvature, the mean curvature, is bigger than that number h0, then I know that all my estimates are right. The roundness estimate, if lambda 1 is small, then I have a round neck, and so on. So I call that the control level. Now, once I know beyond which curvature I have control, I determine the intervention scale. That's a bigger curvature. That's the moment when I stop the flow. So the first time I hit this larger number somewhere on the surface, the mean curvature gets bigger than that large number somewhere, then I stop the flow. I call this the intervention scale. So this will happen, for example, in the middle of this neck, in the thinnest point of the neck or at the tip of the horn. Once I have h1, I have to do the surgery at a larger radius because I have to improve the surface. So in the next step, once I have h1, which I choose really big, I have to determine an intermediate surgery scale, hs, such that it is in a fixed relation to h1. The alpha less than 1 is going to determine how much the curvature is going to drop. Yeah? And I have to fix those three parameters. Now the h0 is given to me by the initial data, and the alpha is given to me by the necessities of making it work, make the curvature drop by a sufficient amount. The h1 is not given to me. It has to be sufficiently large, but I can make it even bigger. All right? So what I'm saying is this procedure will work if you fix the h0 in terms of the initial data, you fix the alpha in terms of the initial data, but then you're free to make the h1 as huge as you like. So you can take actually a whole sequence of surgery constructions where the h1, your intervention scale, becomes larger and larger. In other words, you can go closer and closer to the singularity before you do your surgery. Of course, if you go closer and closer to the singularity, you're cutting out tinier and tinier necks, and you may have to do more and more of these cuts. But each finite intervention scale turns out you only have to do finitely many surgeries. Only as h1 tends to infinity, you may have to do infinitely many surgeries. Okay? That finishes sort of the story there, and it remains to give some hint on what comes in the future. So let me show you the things I'm working on right now with Carlo and with student. So one thing that a student of mine is right now investigating is exactly this behavior as h1. The surgery parameter tends to infinity, and we're confident, looks like it, that we get a convergence of these surgered solutions to the weak solution, level set solution of mean curvature flow that was studied by Chen, Giga-Goto, by Evans and Sprague, and where you have regularity results of Brian White. And the hope is to use this limiting procedures to prove better regularity properties for the weak solution this way. Secondly, it is not hard to transfer the flow to general Riemannian manifolds. You just have to make sure that you find a replacement for the two convexity condition. So for example, if you have a locally symmetric ambient manifold of non-negative sectional curvature, everything I said will go through. Of course, you have to do the analysis and deal with the extra terms, but the extra terms from the geometry of the ambient manifold will not kill the arguments that I described. The really hard problem for the future, I think, is to try to do it for weaker curvature conditions. So the next one is 3 convexity. Assume just lambda 1 plus lambda 2 plus lambda 3 is positive. And then we expect necks, but we also expect bubble sheets, 2-dimensional flat pieces cross Sn minus 2s. And locally, so this could then become a whole Riemann surface of bubbles pinching off. And it looks daunting because then surgery then means you have to sort of cut along a curve inside this bubble sheet and heal the seam of this sheet and retain all the estimates. So it looks like a long-term project, but we are encouraged by the fact that we can prove a roundness estimate, we can prove a gradient estimate, so we have already pretty good control on the curvature level estimates, at the gradient estimates, and get a classification already of some of these bubble sheets and a fairly good description of the bubble sheets. And I think in the future there is a chance maybe in this setting to do a surgery on sheets for the first time. Maybe it's a little bit easier, they say, than Ricci flow on 4 manifolds. So that's the project for the future, and thank you very much for your attention.
In this power generality, would it, I mean, I guess it's essential that every time something is happening that you can kind of lower whatever quantity you're playing with the volume.
The maximum of the mean curvature will drop by a fixed factor alpha, say.
That's going to happen there also?
Well, that's the...
So for the 3 convex.
Oh, for the 3 convex, that's the hard part, because now you have to sort of, in order to make sure that the curvature really drops, you have to make sure that along the whole curve where you want to do the cut, the curvature has dropped by this factor. Therefore, you have to sort of really follow in all directions and control how the bubble sheet widens as you go to the boundary of the sheet.
The worst scenario would be that somehow you're kind of developing a kind of structure of these bubbles where each of them would, I mean, singular, where each of them would just take a tiny bit of energy. You don't have that density. So
Well, I hope that will not. I hope that will, maybe this happens in the very limit, but the idea would again be to already do the surgery just before the singularity, and at that level the smoothness from the parabolic equation is still there, and then I would hope that this does not happen.
In the case that you have proved the main theorem,
Yeah.
you actually give a bound in terms, suppose I give you all the data you want initially, bounds anything you want, can you actually bound the number of times you have to do surgery? Effectively not write it down, but it's effective. Because you seem to have a better situation than Perelman.
Right. There is one step in the estimates which is using a strong maximum principle and a contradiction argument, but I think that can be made quantitative as well. So I would say yes, I can make it effective. Yeah. No, it's not known. No. No.
Is surgery an only option here, or there's another way to go?
Well, there is the big solution. There is the level set solution, right? There is a level. The level set solution is there, but the level set solution doesn't give you the control on the topology. So if you're interested in getting the diffeomorphism theorem, right, to get the classification of these surfaces in terms of diffeomorphisms, then it's the only option I know. And yeah.
Without being paid.
Yeah.
Let's thank the speaker.